Hello everyone, I'm Tang Yingtian. I'm presenting the paper Learning-Aided Heuristic Design for Storage System. The authors are me, Lu Han, Li Xijun, Chen Lei, Yuan Mingxuan, and Zhen Jia. This is a collaborated work from Noah's Ark Lab, Huawei. If we think about the traditional heuristics in the storage systems, they are often rule-based. They have strong interpretability and robustness. But they are also often data agnostic, which means they cannot adapt to the data or the patterns. Examples are as simple as least recently used replacement policy, or FIFOQ. Nowadays, people are using machine learning for storage systems. They are learning-based, they are black boxes, and they are data-aware, which means they can adapt to the data. There are research studies about used reinforcement learning for management of CPU and memory, as well as some research about learned mapping for data indexing. So we can see the dilemma of using ML in a storage system. We want the capability of the ML methods. We want them to recognize and utilize the patterns, for example, the data access patterns, in a specific task or system. But on the other hand, in the real-world systems, we often need thorough sanity checks and complete traceability. So when problems happen, we can trace the problem and fix them. Handcrafted heuristics are easy to interpret, tune, and debug, but ML methods are often black boxes, so it's hard to trace the problems caused by them. In this work, we try to focus on extracting human-readable heuristics from a deep reinforcement learning or DRL agent. We consider a real-time resource allocation problem. The heuristics are extracted as finite state machines, or FSMs. We also provide insights into the extracted FSM to inspire the domain experts. We consider the real-time CPU core allocation problem in our storage product, Dorado V6. It is a centralized and hierarchical storage structure. The I/O requests are sent in and processed by the controllers, and the controllers communicate with the storage resources to complete I/O requests. We only focused on optimizing the allocation of CPU cores that are relevant to this process. In the controller, there are three levels of CPU cores: the normal level, the key value or KV level, and the resource volume or RV level. The I/O request is directly sent to the normal level. If the data is in the shared cache, then the I/O request can be directly processed. But if the cache miss happen with probability, the request has to be sent down to the key value and resource volume level for further processing. Here's another diagram showing the same thing. The CPU cores can migrate from one level to the other. And the normal level basically read and write data blocks from or to the shared cache, whereas the KV and RV level read data from the disk to the cache or write the cache data back to the disk. So the I/O request could be sent to the KV and RV level because of the cache miss or because the write back phase happened. For all CPUs in a level, the tasks are assigned to them in a polling manner. We can describe the workload WFT within one time interval as the following: its I/O size and types, the ratios of them, the total number of I/O requests happened in this time interval, and the probability of a cache miss. But the final one is unavailable to us. It is intrinsic in the data. For every CPU core, they can be allocated to the three levels. When the reallocation happens, a core must first finish the already assigned requests. If there are n cores in total, and for each of them they have the processing capability as m, we can write down the ideal maximum capability as n times m. And our objective is for a sequence of workloads. We have to dynamically allocate the CPU cores in order to minimize the make span k, which is the time to finish all the workloads. If we get back to this diagram, if the cache miss or write back phase happens, the KV and RV levels will demand more computational resources. And if the data blocks can be directly processed, the normal level will demand most of the computational power. So if there's a wise strategy that can wisely allocate the CPU cores, it can boost up the efficiency, so to minimize the processing time. We design our DRL agent as the following. It takes the observation OT, which includes the core distribution and utilization rate of 3 of the levels, and the workload description at time t, and then it makes the decision or the action AT. It is to either migrate one CPU core from a level to the other, or just to perform no migration. And at the finishing time, it gets the reward RT, which is the inverse of the make span. The reward RT applies to each time step with a decay factor. Here we can see the detailed design of the DRL. It is basically a gated recurrent unit that takes the observation and generates the hidden state HT. And then HT is fed to 2 heads. One of them is the policy network and the other is the value network, to generate the action and the estimation of the state value at time t. Overall, the agent interacts with the simulator until the given sequence of workloads is finished. And we train the DRL with the advantage actor-critic method. Basically, for the state action pair, the advantage actor-critic method measures a advantage term, which is the difference between the Q value and V value at this point. And this could be rewritten as the below equation. And in the below equation, we can notice that it only requires the estimation of the state value, and it doesn't need the Q value. So in our network, we can just put a value network there. It is worthy noticing that the state at time t is all the observations from the beginning to the time t aggregated by our recurrent neural network architecture. So another thing that is worth noticing is that once our product is sold to the customers, the storage systems are no longer available to us. But if we are granted with a permission, which is a pretty common business mode, we can collect some summarized characteristics of their real workload. For example, even if the real workloads are unavailable to us, we can collect with the permission the write ratio, read and write ratio, sequential ratio, reaccess ratio, or so on. So using these statistics, we can synthesize the workload ourselves. And in our case, we use VDBench to replace the synthesized workloads. To better train the neural network, we devise a curriculum learning. So the networks are first trained on short workloads with static characteristics, or here we call it easy task. After a period of training, then it was trained on longer and dynamic workloads, or here we refer them to be the hard tasks. With the curriculum learning we proposed, the DRL agent can learn a better policy with fewer training epochs. And here in the picture we can see that the yellow curves is the pre-train process of our curriculum learning method. So basically it's trained on easy tasks at before 1,000 epochs. And after that we shift the model to the harder tasks, and you can see the drop down of the make span or the cost to a relatively low value. But if we directly train the networks on the hard tasks, it takes a longer time to converge, and they converge to a relatively higher value. One thing that we should notice is before the 1,000 epochs, because the yellow curve is training on the easy task, and the easy tasks are generally much shorter than the hard tasks, the 1,000 epochs for pre-training is actually much faster than the training from scratch method. Because if you train from scratch for the first 1,000 epochs, your model performed pretty badly, and the tasks are long and hard, so it takes a long time to finish the episode. After the RL training, we are going to go through 4 more steps for the heuristic extraction or FSM extraction. It includes quantization of the networks and the extraction of FSM. After the extraction, we have 2 ways to interpret the extracted FSM, so the domain experts can understand it better. For the extraction of the FSM, we adopt the quantized bottleneck networks method, which is proposed earlier in 2018. So the basic idea is we have a trained recurrent network, and we have the observation space, the hidden state space, and we have a discrete action. The problem is that for a finite state machine, all its parameters are discrete. So the states are discrete, the observations are discrete, so on and so forth. So the paper actually used a quantization method called quantized bottleneck networks. So they are basically autoencoders that has a specialized quantized activation function in the middle. So they are inserted into the observation space to reconstruct the observation, as well as reconstructing the hidden space. So the effect of this insertion is to discretize the observation OT and the hidden state HT of the RNN. Once they are turning into discrete value, we simply collect this tuple, this kind of tuple, and compute the transition table, and then the transition table itself is actually the extracted finite state machine. More specifically, the QBN is trained with reconstruction error in a supervised manner, and the discretized representations are k-bit quantized and have L as the dimension, size of the dimension. So in total, for each discrete embedding space, there are k to the L distinct values in total. After we extract the FSM, we want to compare the performance by the default product setting, the DRL, the handcrafted FSM, which is a basic rule-based strategy created by ourselves, and the extracted FSM. And we can see that either the GRU or the extracted FSM have better performance than the default setting and the handcrafted FSM. And actually, on average, the GRU is better than the extracted FSM. And it does make sense because the GRU is the original form, and the extracted FSM is the discretized form, which certainly has some performance loss. So here's an example of the extracted FSM of a real workload. Here the circles indicate the state, and in the state here's an action attached to it. The arrow indicates the transition between different states, and the thickness of the circle and the arrows indicate the frequency. And here K, N, and R stand for normal level, KV level, and RV level. The NOP stands for no migration. So we want to interpret the extracted FSM in two ways. The first is to collect the statistics of the transitions into and out of each state. So here we have a state, and the transition into the state and out of the state can be caused by different observations. So what we do here is we collect all the fan-in and fan-out observations and take their statistics for further analysis. The other way is to look at the histories of observations before transiting into one specific station. And we collect all the observation here, and once again we take the statistics and turn it into a time series for further analysis. So here's a specific example. If we just take this visualized state machine and we look at the fan-in and fan-out CPU utilization rate, we can see that for S0, the no migration option is the most frequent state. And it makes sense because FSM adapts to a certain workload, and after the adaptation period is over, it stays at the setting. And if we look at other states, for example, state 1 and 4, we can find that the normal level have the highest utilization rates, whereas the KV and RV level have lower utilization rate at the time step that the transition happened. And if we look at the actions attached to S1 and S4, they're both moving cores to the normal level. And this indicates a basic strategy, that is to move cores with from levels with low CPU utilization to those with high utilization. It's pretty intuitive because we want to move the idle cores from those levels to a level that is highly demanding, that is the normal level in this case. But if we look at the state 2 and 3, they seem to do the opposite. So this is the case that the second interpretation will come to place. So there are three time series. The horizontal axis is the time. We can see that the read workload stay at 0 intensity, whereas the write workload is keep rising. We have another measure called a capacity ratio. So basically, higher the capacity ratio, more requests can be solved directly from the shared cache. If the capacity ratio is low, more computational resources devoted to the communication between disk and shared cache. So for a write request, has a write back phase that has to involve the communication between the disk and the shared cache. And at this point, since all relevant data are loaded and the write operation is performed, it readjusts to empower the write back phase. So it gives more power to empower the communication between the disk and shared cache, so the write back phase can happen more quickly. In conclusion, in this work, we present an integrated pipeline of learning heuristics from DRL policies, and we give the visual and statistic analysis of the extracted FSM, so that human experts understand better what the DRL is doing and what the extracted FSM is presenting, so they can be inspired to devise more complex heuristics. Thank you very much.